Welcome to The Explainer. Today, we're pulling back the curtain on a secret check that engineers use, a way to know if a huge complex problem is even solvable before they write a single calculation. This is the kind of thing that saves millions of dollars, and just as important, a whole lot of headaches.
So, let's start with a feeling I think we all know. That moment when you're staring down a problem and you just hit a wall. Of course you have, right? We've all been there. It's frustrating, for sure. But what if getting stuck didn't just ruin your afternoon? What if it could cost your company millions of dollars?
Well, welcome to the world of industrial process design. Every single factory, I don't care if it's making olive oil or plastic pellets, it's basically a giant, complicated puzzle. You've got inputs, outputs, and a bunch of steps in between. For the engineers who have to design these things, taking a wrong turn can bring the whole project to a grinding, very expensive halt.
So, how in the world do they avoid these massive, costly dead ends? Well, they don't just jump in and start crunching numbers hoping for the best. Nope. They have a simple but seriously powerful check they run first, just to see if the puzzle even has a solution.
I mean, think about it this way, right? You wouldn't start baking a cake if you didn't know for sure you had flour, eggs, and the rest of the recipe. You'd check first. Engineers do the exact same thing, but their tool has a bit of a fancier name. It's called degree of freedom analysis. And what it does is just beautifully simple. It's a quick procedure that tells you if you have all the information you need before you dive into hours of complicated math. It's like checking the map before you start the road trip to make sure the destination actually exists. And the process itself is super systematic. Step 1, you draw a picture of the problem, a flowchart. Step 2, you count up all the things you don't know, your variables. Step 3, you count up all the things you do know, basically your equations or relationships. And then, the final step, you just do a little subtraction. And the number you get from that subtraction tells you everything. If you get 0, that's the magic number. It means your problem is perfectly set up. You have just enough information to solve it. If the number's bigger than 0, you're underspecified. You're missing a piece of the puzzle. You need more info. And if it's negative, well, that's overspecified, which means some of your information is probably wrong or just repeating itself.
Okay, that's the theory. But let's actually see this thing in action, right? Let's put it to the test with a couple of real-world examples.
Okay, so picture this. We're designing a pretty simple olive oil extractor. Olives go in one side, and oil and solids come out the other. The question is, can we figure out the flow rates of that oil and those solids?
All right, let's follow the steps. First, what are our unknowns? Well, we don't know the mass flow of the pure oil, and we don't know the mass flow of the solids. So that's 2 unknowns. Next up, our equations. We can use a basic law of physics here called a material balance. It's just a formal way of saying what goes in must come out. We can write one balance for the oil and one for the solids. That gives us 2 solid, independent equations.
So, what do we get? 2 unknowns minus 2 equations equals 0. The degrees of freedom are 0. Bingo! This problem is solvable. We can now confidently move on to the actual math.
Awesome. Now let's try another one. This one looks pretty similar on the surface, but you'll see we get a totally different answer. This time, we're making a specific plastic pellet by mixing 3 different things together.
Okay, let's count our unknowns. Here, we don't know the starting amounts of 2 of the things we're mixing in. And on top of that, we don't know the exact recipe, the weight fractions of 2 components inside one of those streams. So that's 1, 2, 3, 4 unknowns in total. And our equations? Well, we have 3 components. Let's call them A, B, and C. We can write a material balance for each of those, so that gives us 3 independent equations. And here's the moment of truth. 4 unknowns minus 3 equations leaves us with 1 degree of freedom. This system is underspecified. It's unsolvable as it is right now. And think about what that check just did. It saved us from hours of uselessly spinning our wheels. It told us, hey, go find one more piece of information before you go any further.
Now this whole degree of freedom analysis thing, it's not just some random party trick. It's actually the very first and maybe most critical step in a much bigger, systematic way of solving these material balance problems.
And you gotta love this quote from the source material because it just hits the nail on the head. The whole point of having a system like this is to make sure you spend less time just staring into space, scratching your head, and more time actually solving the problem.
So,
Look, knowing a process is solvable is great. It's a huge first step. But at the end of the day, for any real-world business, there's a much bigger question. So what? Why does this even matter?
This is where the engineering hits the economics. Let's go back to our olive oil plant. Because we knew that problem was solvable, we can now calculate exactly how much oil we can make and how many olives we need to buy. And once you have those numbers, now you can talk about money.
The very first economic check is something called gross economic potential. And it's really simple. You take the value of everything you sell in a year, in our case, $1.5 million worth of olive oil, and you subtract the cost of all your raw materials, $1 million for the olives. What's left over is our GEP, $500,000 a year. And that leads to the final payoff. We can take that GEP, subtract other costs like electricity and labor, and get our net profit. Then, we compare that annual profit to how much it cost to build the whole plant in the first place. For our little olive oil plant, it turns out we get a 20% annual return on our investment. So the puzzle wasn't just solvable, it was profitable, it was worth doing.
So this simple check, this degree of freedom analysis, it's really the key that unlocks everything else. So the next time you pick up any product, your phone, a can of soda, anything, you can ask yourself, what was the puzzle of inputs and outputs they had to solve to make this? And was it a puzzle worth solving?